engineers and electrical safety. So what is NFE? It's all about creating awareness on electrical safety, which was born in the month of March. So we are nearing 1 year. We have achieved many milestones in last 11 months, I would say, 11 months. And we are considered to be one of the fastest growing society in India, where we have more than 1,000 members, a lot of electrical consultants, architects, contractors, manufacturers, they're all joined together. And we expect it to grow over 2,000 to 3,000 in the next couple of months. NFE, again, we've been crusading, the topic on better tomorrow, making our nation electrically safe. And our vision is very clear: to make every electrical installation free of accident, such as electrocution and fire due to short circuit, and thus contributing to the saving of lives and property and supporting sustainable development. Mission: we shall strive to achieve our vision through getting accredited for products and personal certification. This is something very strong agenda for our president. And this personal certification, we shall focus on electrical safety by design, manufacturing, installation, and maintenance of electrical product. Installation by competent, I underline this, this is very much required in India. Installation by competent, qualified manpower using quality resources, including product, process, and procedures. That's the mission of the NFE. What we do? We are going around creating awareness on electrical safety, improve skill of practicing electrical engineers, improve safety measures followed in the industry, introduce modern safety measures of engineering, and improve quality of electrical installation. I would urge those who are not yet become a member of NFE, and today being a free webinar, I'm sure that many were non-members who have joined today. Please visit our website, and very simple, there is a link there, become a member. Less than a minute you can become a member. We have individual membership, we have corporate membership for all the OEMs, and we have MSME for Indian small scale industry. We have completed, this month, this year, I would say in January, we spoke about an earth electrode, and we did a seminar in Nagpur. We just completed one more seminar in Vadodara yesterday, well attended, over 160 professionals attending the program. So we have upcoming seminar now in Chennai on 16th, that is next Friday, and followed by 23rd in Goa and Mumbai on 15th. So those who are from this region, if you are not yet received the invitation, please do join. In Chennai, we'll be doing it in Radha region, Coimbatore. So please do attend, and you can meet us. All the speakers will be there. And just recently we completed on a CA regulations on electrical safety audit. And 27th of January, Mr. Appavu conducted CA regulation, the role of distribution companies and stakeholders in minimizing fire and electrocution, well attended by our members of NFE. Today, we are talking about power quality and harmonic distortion. Why this subject? My name is Dominic here, and I'll be hosting this, and we have a great experts today joining us to discuss on this subject. So today we are specifically clear up what is power quality and harmonic distortion. We look at why they happen, what problem they cause, and most importantly, how we can fix them. Thank you so much for joining us, and your participation shows you care about the quality of power and the system. And now let's get started. Feel free to put up your question answer. We have the, if you look at below, there is a Q&A box. do not put it on chat box. Chat box will be difficult for us to record your question. I would request every participant to put their question. Our moderator, Mr. Gopakumar, will take up this question and make it more interactive. And we have our president, Mr. Gopakumar, today, and he's the founder of Cape Electric, Cape Power Productions, OBO Betterman, and LP Consultant International. He is also a very active member, technical committee of BIS, ETD 20, ETD 30, ETD 50, and also a member of National Building Code, and is quite active in International Electrical Code, TC 64, TC 81, AC 37. So he's a well-known face, and he's been there in every webinar. I think we have done more than 300 webinars, and quite well-known personality we have, and also is the president of NFE. We have a great speaker. He's joined us from Dubai. Very rich experience, Mr. Hari Balasubramaniam. He's a passionate energy management expert with over 30 years of experience in India and Middle East. He has relentlessly served customers in the region by providing technical consultancy beyond the business development profile he handles. Having worked with many European energy management and power quality measurement companies, he is continuing his support to provide customers in India. He believes only continuous knowledge sharing can provide perennial improvement and increased energy efficiency among consumers. Hari is thorough in his energy management solution that blend the appropriate device for monitoring communication possibilities and software with result-oriented analytics. He is very much interested in energy management, power quality, and residual current monitoring, which is encapsulate the full cycle of energy management activity. I now welcome the opening remarks by our President, Mr. Gokumar, then followed by Mr. Hari on the subject that he wants to speak. So, over to Mr. Gokumar, sir, if you are there, we would like to have a few words before he begins.
Good morning, all participants. Today, we are making a webinar on a new subject, probably in our platform. So far, we were talking always about electrical safety. This time, we are talking about power quality. We have a great speaker, and first, without wasting time, let us start the presentation. You can share the presentation and start it, please.
Yeah, I will. Okay, sir. You will go on mute.
Yeah, I will. Should I share the screen?
Yes, please. Yeah, it's visible. Full screen.
Is it visible? Good. Thank you. Thank you.
Yeah.
Namaste, everyone. I'm really excited to be in this group. In fact, on a Saturday, close to the afternoon, I see such a good attendance on this kind of a webinar. I'm really thrilled to be with you all, and thank you for giving me this opportunity to share my thoughts on the power quality and harmonics in this webinar. Thank you very much, NFE. Just as I start going into it, we have I have an analogy of water quality. Usually, water is a commodity which is distributed, stored, and then again distributed into various consumers. So the quality of the water, what we get, can get transformed at every level. So over a period of time, so the water comes, again it is saved for maybe few days, and then it is for few hours and then distributed again. But in case of electricity, as we generate electricity, we also consume electricity. At the same rate, assume that we are also polluting the electricity. Yeah, polluting the grid, in other words. So this is a very fast phenomenon which is happening on the power quality on the electrical side. So this is always the analogy. In fact, what we see is the water quality, we see it, but we do not, most of the time, we don't see it as a quality of water visually, but it is in other forms, maybe by some shutdowns or through some burnout of some components and things like that. So that's what we are going to discuss today. The term power quality refers to a wide variety of electromagnetic phenomenon that characterizes voltage and current at a given time, at a given location on the power systems. And it can be classified as conducted and radiated. And we will discuss most of the conducted low frequency phenomenon like harmonics, voltage fluctuations, voltage interruptions, voltage imbalance, and things like that, and also with the respective standards what we can follow. So this is what we are going to do today. So this is for a very simple system, assuming that we have one of the user with non-linear loads and another user with a linear loads from a network. So what happens here in this case is when a linear load, non-linear load gives an output or pollutes the frequency harmonic like this, or the waveform like which is on the left side of the screen, the right side user gets a different kind of, he too doesn't get a sine wave. In other words, you see a distorted sine wave on the other side. Say, for example, I can show you the screen again and before. The user one uses non-linear loads, and because of that, he pollutes, he discharges a non-linear current waveforms into the grid, and because of that, the voltage gets corrupted, and then that voltage provides a current, so provides as a current source for the linear loads, which is the user 2, and then he also gets a very bad waveform. So this is a very simple way of informing that the harmonics can be flowing from one load or one consumer to the other, where it can affect the performance of the machinery for no fault of the linear load consumers. Yeah, this also has repercussions down below. So what makes the harmonics flow from one to the other, which means we have something called, we call something as an impedance of these circuits upstream and downstream, can potentially have an effect on the harmonics, how it is transmitted to the other consumers. So if the grid impedance, the grid is very dynamic. Normally the impedance of the grid changes continuously depending on the load, depending on the connections. Then in these situations, then we also have the weak grid and robust grid. The strong grid probably can assume or can observe certain amount of garbage from from the industries, but the weak grid cannot do so. The position of the industries or the load in the grid also matters, whether it is in the weaker grid or in the robust grid. How do we do it? We will find it out in the next coming slides as well. Yeah, so this is the robust grid. In many places, if we have a very good grid, then we can also throw some harmonics, which is essential for us to make our efficient systems with some kind of VFDs or some kind of drives, so that we get a higher production. But at the same time, if the grid is weak and if we use the same kind of equipment, then it can potentially not only affect us, it can also affect the nearby consumers who are going to do it. So that's the part which I wanted to put it across. Whatever it is, if you can't measure, we can't improve it. That's what we say. That's what Lord Kelvin said. So when a power quality is bad, what can happen is what I wanted to say. When a power quality is bad, we can have tripping in your systems. We can have control systems hanging up. We can have production failures or batch failures. In batch processing industries, this is much more much more sensitive because many times they lose the whole raw material what they put in. Yeah, so it becomes very, very important that the batch processes happen continuously, especially something like in a paper industry, for example, or a pharma industry, where we have batch processes and you put the raw material, and then for some reason of unknown reasons of power quality, if something fails, then we also get into the trouble of losing the raw material. Yeah, so that's the thing. And harmonics or the power quality can also reduce the lifetime of the operating equipment. In fact, many times it so happens tripping happens without any reason, so that is also a possibility of doing it. And moreover, harmonics or the power quality effects can cause heating in the system and in turn reach up to the stage of fire as well in sometimes. Yeah, so but this needs to be taken care, and it needs to be addressed very, very urgently, as we have more and more loads coming up with which can throw harmonic potentially into the grid. So I can classify these power quality parameters into frequency, magnitude of supply, flicker, unbalance, voltage harmonics, and current harmonics. And then once in a way, events which can happen as voltage interruptions, sags, swells, and transients. So we will see some of these points over here. Let us see the sags and swells, which is very common. A sag or a swell is a very short-term voltage drop below 90%, or the swell is a voltage high above 110% of the nominal voltage. These are all as per standards or given for that. We will see those standards also, EN 5160 and IS 17036. I think it is an equivalent of EN 5160 in India. And then we also have 90% of the nominal value, which when the voltage reduces for a very short time, for a half cycle to 1 minute. So this can also be classified as sag. That's what in the next slide it says. A voltage dip is classified as from 10 milliseconds to 1 minute as a voltage sag, and then beyond 1 minute, it can be called as an under voltage also. Terminologies vary from country to country, manufacturer to manufacturer, but what remains is the crux of the information, that there is a voltage under voltage happening between 10 milliseconds, and it can go higher and higher up to whatever the time we have. Say, for example, voltage dips are generally considered, sags are considered as an event which happens between 10 milliseconds, which is half cycle to 1 minute in a 50 hertz network. On the right side of the screen, I have something called as ITIC. So Sebima curve is again a standard which gives a nominal voltage working performance and the critical voltage areas. So when the voltage goes for a short time, the x-axis is the time and y-axis is the percentage of the nominal voltage. And then if there is an event which is happening within the critical voltage area, whether it is over voltage or under voltage, then we can probably find out how many events are happening on the over voltage area and how many are happening under the under voltage area, and then we could take possible solutions which we can see to reduce these kind of events, so that the equipments what we use are safer. Say, for example, if a voltage low occurs very constantly for 100 milliseconds, I'm just giving an example, and the voltage goes low around 50% for very few cycles. 100 milliseconds is 5 cycles approximately. So our motors can take higher current during these times. The VFDs will not know why the voltage is going low, and then it can behave erratically. So these kind of things can be sorted out by plotting it properly in these kind of a curve and understanding how these things occur can be much more easier for us. So that's about the sags and swells on the system. A sag, as I said, is the voltage level going for a very short time. In the screen, what you have, the voltage going low of around 73 volts from a 230 volts to 730 volts, and then it goes back within 302 milliseconds. So 300 milliseconds it goes back. So this is a phenomenon which can happen in these networks. Or the swell here, which is going up to for 1 second, 1000 milliseconds, 1 second. So up to a voltage of 284. So this is also not good, and the previous one is also not good for us in sag and swell. So this is how we can understand sags and swells. Sag and swell are most common in our networks when the grid is weaker, when the transformer is fully loaded or working to its capacity, and a very small increase in short-term increase in loads or a starting of a motor can also create a sag in the network what we are under. And then it comes to a voltage interruption. Voltage interruption is usually defined as when the voltage goes below 10% of the nominal voltage, and then it is said to be voltage interruption, and this should also be recorded and found out. And generally it happens as a power supply failure, where you don't get the voltage and then the voltage goes to zero. But generally it is not 0%, it is actually 10% of the nominal voltage where these equipments are designed for. Current and voltage unbalance is the next topic. This is again, if the phase shifting is not 120 degrees, or the current is not equal in all the three phases, or the voltage is not equal in all the three phases, can have an effect on the systems as well. So there is a ways to ascertain what is the unbalance in the voltage, what is the percentage unbalance in the voltage and the current, and then we can probably take action based on that. So when the current is not equal, yesterday someone was asking me, I have a current in a motor consuming 300 ampere in one phase, 250 in others, and then I have 225 in another phase. So this is a clear unbalance what we have seen, and then we have to ask them to go and do some more inspection on the motors to check why it is consuming differently. It was a star delta starter. So these kind of things in unbalance can also cause problems in the circuit, and harmonics or the power quality can also play a vital role in creating an unbalance in the circuit. So that's how, especially when we use more number of electronic lighting systems in single phase, three-phase circuits, then, and if it is not distributed, we have more problems to come, as the neutral currents can potentially increase. And I have an experience when the neutral current was increasing, and then the neutral cable burned, and then they said, oh, this current is going high, put 2 runs of neutral cables. So these kind of solutions is not actually a solution, it is only some kind of a fix, because it is in no time the second cable also start getting heated up and then starts burning up. So this is a very common phenomenon we need to understand on the unbalance of the circuit. Transients is the next topic, which happens usually within a cycle. So within a sine wave cycle, or within a half cycle, 10 millisecond time, the transients can be oscillatory, or it can reach to a peak and then reduce it also. So both these kind of transients are not good for the systems, because the insulation gets weaker when these kind of transients happen commonly in a circuit. So wherever there is an insulation fab can easily weak can get ruptured there, and then it can create a short circuit. So that's the next part of why transient should not be avoided. So I wanted to also take a time to see how the transients are measured in the whole system, or how do we measure the transients in this case. Say for example, in a normal sine wave form, we take samples. Say for example, we take every 40 microsecond a sample within the 10 millisecond half wave or 20 millisecond full wave form. Then the transient can be happening depending on, in a normal sine wave, you have every 40 microsecond, the value is fixed based on the voltage. But if there is a change of 10% plus or minus, then it can be classified as a transient at that particular sample. So that we call it as an absolute sample. And the difference between the two samples, the delta between the two samples, is also fixed in a sine wave. So if that again varies, that can also be classified as a transient. So that is how the transients are calculated in any of the metering equipments in this case. Yeah, so that's about the transients. Coming to our favorite subject of harmonics. Harmonics are the superficial different frequencies, or the multiples of the frequencies of the fundamental. So if you have 50, 100, 150, 200, 250, so it or ranked as one class fundamental frequency is 50, and then it goes 100th frequency is second harmonic, third, fourth, fifth. Fifth is 250th frequencies, and then we start getting these kind of when waveforms superimposed on the frequency, thereby the original frequency what we get is getting distorted. So I will go back to the slide. Say for example, you have a third, fifth, and seventh harmonic. The blue color waveform is the main waveform, but when these frequencies of third, fifth, and seventh harmonic are superimposed on the fundamental waveform, then you have a problem, because the fundamental waveform changes according to the noise and the amplitude of the harmonic currents what we have. Yeah. So how do we classify the harmonics? There are only, till now, most of us know a parameter called total harmonic distortion, which takes into account all the harmonics present in the waveform. Yeah. It means there is a phenomenon called fast Fourier theorem, which is applied on the frequency sample what we are getting, and then we divide those frequencies, different frequencies, with the fast Fourier theorem. So that's how the harmonic is calculated, and then these harmonic are totalized with a formula and divided by an x. I will show you the formulas right now. So then it is called as total harmonic distortion. So in a normal case, if I'll 1 minute. Yeah. So you have a spectrum of frequencies, harmonic frequencies, with which you have 1 to 63rd or 1 to 30. And then based on these frequencies and the harmonic content, we calculate the total harmonic distortion. So total harmonic distortion is calculated for the harmonic frequencies, so which is in this formula, which is said as m, the ordinal frequency what we measure. That is depends on the Fourier theorem how we use it, and then out of this we take the m up to the frequency of m. M is basically, it can be 50th harmonic, 63rd harmonic, depending on the device, or 30th harmonic or 15th harmonic, depending on the measurement device. And then they calculate based out of the fundamental value, say I fundamental or V fundamental. So which is based on the existing load. Yeah, so existing load. So this happens, and then we get a value for THD, total harmonic distortion. In the later, as the IEEE 519 evolution happened, then they also introduced a terminology called as TDD, total demand distortion. So the total demand distortion means it takes based on the value called IL for the current, especially not for the voltage, but TDD is only for current. And based on IL is basically the average current over a period of time. Say, for example, 12 months average is considered as a load current. Say, for example, so that you know this is your average load and what kind of harmonic you are generating based on your loading factor rather than on the fundamental where it can be either low or high. I will also show you a simple screen here how a load current can load current with a total harmonic distortion, THD, is shown here. If you see the red color graph is the load current, and THD is the blue current. So if you see when the current goes high, THD goes low. When the current goes low, the THD is going higher and higher. Especially you can see at the end in this kind of area where the THD is slightly higher. So which means, can we take THD as a parameter, total harmonic distortion as a parameter, to ascertain that whether we have a more harmonic or not? No, it is not possible. We may have to take the parameter called TDD. If you look at it, TDD varies along with your loads most of the time. So if your load is high, then the TDD also goes high. And if the load is low, TDD also goes low. So in this kind of phenomenon, now I will try to compare between THD and TDD also here. You see here, so for what you will do the compensation, whether you will do the compensation for a total harmonic distortion or a total demand distortion. This is a question which I put forth for us to think about it. Yeah, maybe we can discuss it over a period of time or by the end of the session as well. So we have the total harmonic distortion and total demand distortion, which we need to understand so that we can take appropriate action. Total giving a solution with total harmonic distortion cannot give us a right solution. This is what is my opinion. We can always check this out. But total harmonic distortion is also comprised of all the harmonics built in. So when we are measuring THD or TDD, it is very important for us to know up to what frequency or what harmonic content these THD is calculated. So this is very, very important. Say, for example, you have a device which calculates THD, and it only finds harmonics up to 15th harmonic, which means the device should naturally be taking only considering only up to 15th harmonic for THD calculation. So this is a very important point which we need to understand. So while we measure the harmonics, while we measure THD, we need to know up to what harmonic, ordinal harmonics these device measure, and then how it is the THD and TDD is calculated. So this is about THD and TDD for us to understand. Now I come to the standards. I always say standards, adhering to standard is not a choice, and it is in fact, it is the lifeline for all the electrical systems. Yeah, and I'm very happy that NFE is promoting so much of safety in the systems, and I'm really excited to be a part of NFE for this matter, at least. Yeah, so this is where there are various harmonic limits, there are compatibility levels, and then testing and measuring standards. So there are quite a lot of standards which are already developed in IEC. It is already developed a standard for measurement. There is always a compatibility measurement, compatibility levels for the equipments are also there as an IEC standards set in over here. Say, for example, in a circuit, the incoming level or the voltage characteristics in the public grid or in the distribution network is characterized as EN 5160 or IS 17036, I think, for Indian standards, yeah, which is a characteristics of the voltage. And then when it comes to the PCC level, where the consumer is taking power into his system, that is called as point of common coupling, there the system like standards like IEEE 519 is applied. And then at the compatibility level of the equipment, you have 61000-2-4. So these are all the power quality limits where EN 5160 will talk about voltage, frequencies, and stuff like that. IEEE 519 will talk about current harmonic and voltage harmonics. The 61000-2-4 will talk about the equipment level harmonic emissions which can be possible. Say, for example, I wanted to say, if an equipment manufacturer says that I am IEEE 519 compliant, that is a PCC, yeah. But how come that standard can be applied to that equipment which is in the consumer premises? So in this case, we have a point that what we can understand is, if there is no other loads in the consumer's premises and he is directly connecting it at the point of common coupling, then this complies to IEEE 519. Yeah. So we will also go through, see the IEEE 519 standards in a very brief manner in the coming slides. Yeah. So this is just the how it says. So the more the loads, more the EV charging, more the VFD loads coming in, then we also have to see these standards are complied by the equipments, and it is meticulously followed in doing it. Many of the European countries have different standards adopted or being followed, but in India, we are still catching up with with those kind of standards and implementing it. The implementation of the standards comes from the project stage and not from the operation stage. If you don't do it at the project stage, then we lose it at the operation stage phenomenally. And then most of the time, operations would not have budgets to, upgrade the systems most of the times, yeah, or there would be a lot of it goes through its own difficulties. That's how it is. So there are few standards here which we will discuss. 61000-4-30, which is testing and measurement techniques for power quality measurement methods. EN 5160, which is the characteristics of the public distribution voltage. 61000-2-4, which is EMC compatibility of all the industrial plants and the equipments which they are using. And very interestingly, the most talk about standard IEEE 519. In 2014, it was called as recommended practices and requirements for harmonic control in electrical power systems. Now they have come back and said, no, it is no more something like a guideline, but we call that as a standard for harmonic control in electric power system. So there is a shift, the way in which the wordings of the standard head title itself, which means it needs to be implemented. As I said, it is no more a choice. It is no more a guideline. It has to be implemented in the consumer premises. So that's how it is done. I talk about EN 5160 is as I said, it is the mains voltage characteristics, which talks about frequency, magnitude, waveform, and the symmetry of the three-phase voltages. This is what it talks, and it has its own limits. It is measured over a period of 7 days time. So usually EN 5160 is measured over 7 days period. So the frequency is measured every 10 seconds. And then the magnitude, waveform, voltage is also measured every 10 seconds. And then there are different standards for it, different limits for it. And then for short paucity of time, I'm just giving only the headlines so that I can discuss more about IEEE 519. We can also discuss in later on. If you need more information, I will be happy to share with you on EN 5160 and 61000-2-4. So 61000-2-4, which is for equipment, it talks about voltage deviations, it talks about short-term interruptions, it talks about voltage unbalance, it talks about interharmonics up to 50th order. EN 160 talks only about the voltage harmonics up to 25th order, and then the transient over voltage. So it can be classified as class 1, class 2, and class 3 as well, the 61000-2-4. Now, this is very important to know that there is a measuring standard for harmonic measurement, which means how do we measure harmonic? Because not harmonic measurement is more of a calculation. As I said, it is a Fourier theorem. Yeah, so different people or different manufacturer could follow different calculation methodology and the sensing methodology, so that there may not be much of a uniformity. So that is why the standard specifies two class of devices called as class A and class S. So class A means it is a legally valid measurement methodology which can stand in court of law. Class S has given some kind of room for the manufacturers to go about their way. Yeah, so that's how the class A and class S standards are defined in this particular standard. So 61000-4-30 defines the correct measuring algorithms to be used in the instrument, and it meets the highest performance and reliability of the measured values. That is why I said that it can be in it is legally valid class A standard. Yeah, and then you also talks about different kinds of measurement can also be used by some kind of a leverage for the manufacturer and the electronic circuit, so that those meters are called as class S. So when a class A device, two device of class A with same configuration is put in the same location or in the grid or in the circuit, then it is supposed to measure and give the same kind of harmonic values, both the sides. Yeah, so both the device should give the same harmonic values. So that's how the 61000-4-30 is designed. So it talks about IEEE 519. Actually, when it comes to it, it actually talks about different kind of practices which clearly demarcates who is responsible for what. So if the voltage harmonic is the responsibility of the distribution companies, and the current harmonic, because of the loads, they generate current harmonics, and they are the responsibility of the consumers. So it very clearly demarcates this, and it goes to all the voltage levels. So that is very important. It goes at different stages of voltage level, and it also goes at various stages of the where your grid is positioned, which we'll be seeing it in the next slide. So for the purpose of measuring harmonic, when you are doing the harmonic measurement for IEEE 519, we need to use only class A device. So this is very clearly defined in IEEE 519. It should be measured in the point of common coupling. That is where the transaction of power happens between utility and the consumer, and it needs to be measured at that point, and it has to be statistically evaluated for on a weekly basis and also on a daily basis. There are limits specified for a weekly and also on a daily basis in the standard. Say, for example, as I said here, the class A device needs to be at point of common coupling. And by doing this, we are we are making the grid stronger. In other words, I'll put it like this: when we are complying to this IEEE 519, we are making the grids more stronger. When the grids are becoming stronger, we don't have any problems of voltage issues. We don't have problems on breakdowns in our plants. We don't have we have a longer life of our equipment and machineries, and we mitigate the risk of fire due to harmonics in our system. So there are quite a lot of benefits of following standards like IEEE 519, but thereby we make our life much more easier in running an operation. um, I the IEEE 519 gives a sampling. It also tells you how the sampling should be done for calculating the harmonics and how the measurement should be done. Say, for example, it talks about a sampling should be done every 10 cycles and RMS value calculated for every 10 cycles, which is 200 milliseconds in a 50 hertz network. So we calculate RMS values for every 200 milliseconds, and we store data every 3 seconds, averaged those 200 milliseconds over a period of 3 seconds. And then we also have averaged values for 10 minutes, the 3 seconds values, so that these are all stored for all the harmonics, which means THD, TDD, and also the individual harmonics are stored, and then done a statistical evaluation is done. So how do we do the statistical evaluation? Measurement is done every 200 milliseconds. As I said, every 3 seconds it is aggregated, and then on a daily basis we calculate the 99th percentile value. So this is one statistical evaluation which is done, and then it has its own limits. So the daily evaluation of 99 percentile has its limits, and then you have a 10 minutes value which is taken from the 3 seconds value aggregated, and then again you calculate for a weekly evaluation of 99 percentile limits and 95 percentile limits. Why we are having these three values is the next question. Why should we do three statistical evaluation in these calculations? When the standard was formed, they wanted to make sure that every kind of loads adheres to this. So that's why a constant load can be very easy. It can very easily pass in a 99 percentile daily values, but weekly values, they can potentially fail. For example, a textile unit can probably can pass with 99 percentile evaluation limits, but they might have troubles in weekly evaluation limits with 10 minutes values, or vice versa for a furnace. So in a furnace industry, probably it can fail on a 99 percentile, and it can also pass sometimes on the 95th and 99 on a weekly evaluation. So the amount of data what we are handling with these standard is humongous. Yeah. So which means the 3 second value what we are collecting on a daily basis per parameter. So what all the parameters we collect? TDD, harmonic 50. So harmonic, current harmonic and voltage harmonic, that is 300 values for all the three phases. 300 plus 300, 600, 300 values. And then you have THD and TDD also. Yeah, three phases. So which means around 306 parameters for 3 seconds, which means in a day you have 28,800 samples per parameter, and that needs to be percentile wise, it should be calculated. So we should find a percentile for that, and then compared with the table what is given in the standard. For example, I have shown here the standard of 120 to 69 kV. What are the standards? So TDD is having multiple limits depending on how your loading is, how your where you are in the grid is. Say, for example, If your ISC by IL, ISC is the short circuit level at the point of common coupling, and IL is the average load over the 12 months period what we have consumed, which I have talked about when we are talking about TDD. So depending on ISC by IL value, that is the position of the strength as per the strength of the grid what you have at that point of common coupling, the TDD value varies. Higher the standards, thereby we have the higher the standard, we have a higher the ISC by IL value, you can have higher TDD values as limits. So there are multiple limits which needs to be followed for the IEEE 519. So as I said here, you see total number of samples, we can say 28,800, out of which it can cross the limits 289 times. So approximately, so there is a leverage. In other words, if I say that we can cross out of 28,800 samples, we can cross the limits roughly around 289 times. Whereas the same way, when you consider it for a 10 minutes value for a weekly period, then you have a sample per parameter, 1008 samples, and then you could probably have 10 overcuts for 99 percentile and 50 overcuts for 95th percentile. So now, why we need to see 3 seconds and 10 minutes data in an IEEE 519 is the next question coming up. You can see this graph here where you have a 10-second values recorded for TDD and a 3-second values recorded for TDD in graph in gray. 3 seconds value is in gray, and the orange one is the 10 minutes value. So the limits are different. As I said, the limits are different for 3 seconds values and for 10 minutes values. So this gives a clear idea that if our voltage or the information is very much fluctuating, then the limits are high and we can still follow. We will be in a position to follow. So there are 3 limits which we need to consider for when you are monitoring for IEEE 519. That's about this. So in other words, you can say the last 1 percentile value can be beyond a certain value. So I have just put, if that is a 3 seconds values, how the 99 percentile times you are within should be within the limit, and you have 1 percentile time you can be above the limit also to pass with an IEEE 519 standard. So this graph explains very clearly how the percentile calculation is done as well. Now, do I say that IEEE 519 is for all the circuit, even if I am having a generation in my circuit? No, it very clearly talks about if there is a distributed generation happening greater than 10%, then there are other current limits which needs to be followed. Like IEEE 1547 or 2800 can be applied. But if the generation is less than 10% of the average load demand, then we need to follow the IEEE 519. So there is also a classification. Why I'm saying this is because now a lot of industries are consuming or also having solar power generation as a part of their system. So if it is at site 10% and more, different standard should be followed. If the solar generation is less than 10%, then IEEE 519 can be very well followed for this. So before I close, I will talk about few more parameters, like some of the myths what we understand here. What is the best sampling rate or accuracy what we can have while measuring harmonics or while measuring? So very interestingly, IEC 61000-4-30 says sampling rate should therefore be at least twice the maximum frequency of the waveform, which means it says 100 sampling frequency, 100 100 hertz can be the sampling frequency, but for 100 samples per cycle, then you need to have 5 kilohertz. So this is a very simple sampling frequency, and the samples per cycle is basically the sampling frequency divided by the frequency is called as samples per cycle. So for example, if I have a 5 kilohertz signal sampling frequency, then in a 50 hertz and 100 samples per cycle is what would come. So sampling rate would be every 200 microseconds. So that's how it is calculated. But there is no specific sampling frequency suggested by any standard till now on the for calculating or measuring the harmonics. So this is what I can say. So probably we would say 512 samples for a very reasonable device, or a 256 samples can also be a reasonable for a good power quality meter. And all my MCC complies to IEEE 519. This is another myth. That is, as I said, an equipment manufacturer would say, I comply with IEEE 519, which means when they consider no other loads, but they consider only one load, which is their equipment at the point of common coupling, then that is clearly defined as to be within the range. Yeah, but that should not be calculated. It should be actually according to IEEE 61000-2-4. Yeah, so that's the second part of it, and which needs, because these are all basic information which I thought I should give. So as I said, THD and TDD commonly used terminologies. TDD depends on the IL, and THD depends on the fundamental. So we will have differences where we have when we do an mitigation activity for a harmonic with THD, and TDD can produce different results. So we need to be aware of this as well. Yeah. Then connect PQ monitor for 1 day and check the compliance for IEEE 519. No. As I said, that's a myth that I do the power quality monitoring for 1 day and then do a power quality study and say I am complying to the standard or not. No, as I said, we have to take 3 kind of statistical evaluation. One is for 1 day and weekly, 95 percentile and 99 percentile, which is defined in the standard. So if the IEEE 519 measurement has to be completed, we need to have 7 days of daily values and then 1 week of values to completely comply. So you will have 7 days pass or fail for a daily values, and then you will have weekly values as well for 10 minutes taken every 10 minutes for you to say determine whether it is pass or fail as per the limits. So this is just a small information which I thought I should be able to give it. So I think I slightly push forward myself to give room for more discussions, and I will leave it open to see that if there is any questions to be taken. So
I would urge participants to put your question in Q&A box so that we can take the question. And anybody wants to interact, raise your hand. There is a raise hand symbol is there. You can have interact directly with the speaker and the moderator also.
Yeah.
Sir, over to you, sir.
Hari, there are 2 questions. There are a few questions. I'd like to take some of the questions. But before that, I would like to ask a question which is probably in generic nature.
Yeah.
Regarding this harmonics.
Yeah.
So if you can unshare, would be great.
I will do it. I'll do it. 1 minute. Yes. Yeah.
So normally in other countries, when we go for this IEC meetings and all, harmonics is not a big subject of discussion in those countries with respect to the point of common coupling, or the distribution company or transmission company is concerned. So I had a few discussions with some of them, and what I understood is finally the equipment, the connected equipment or the electrical appliance is creating harmonics. And in those countries, the amount of harmonics which these devices are generating has to have certain limit. That means at the source itself, the harmonic generation is limited. Once when the harmonic generation itself is limited, the effect of this harmonic into the entire network is also automatically reduced. Whereas, if I say that in India, we don't try to reduce at the point where it is created, and we try to go for low quality product and produce more and more and more harmonics, pump it into the entire or create the entire network, with a kind of unwanted harmonics or power quality things, and then we try to filter out at one point a lot of monitoring, lot of filtering. It's a kind of not a healthy situation. What is your say on this?
That's what I say. When at the time of project, that's what I said during the discussion itself. At the time of a project, if the right equipment is chosen, and then it is normal in European countries to follow IEEE 519 standard. They don't, if which is effortless in their specification, whether they state or not, it has to be followed. The equipment needs to be 61000-2-4 certified. These things automatically comes into picture. Whereas during the time of project, as a part of the specification, and it is meticulously followed. But in our country, unfortunately, we go behind reducing cost in some way or the other, and then thereby we tend to get the components with a kind of this can solve our issue and we can go and do the project very quickly, and then this kind of equipment invariably leaks into the system and starts getting installed, and then we can't get out of it so easily. so once you say that this particular X amount of drive is enough for me to run my plant, rather than looking at whether I am using it in a more less harmonic generating base, then in that sense we will have we are still yet to be there in that kind of a way. So we are still policing for harmonics. If you look at it, we are looking for regulations to come in for harmonic regulations, then we will follow. But in European countries or in American countries, it is a normal system that follows the takes that I need to be following up the system in the standards. So that's where the main difference comes in.
Yeah, that means the quality of the products are meeting certain distortion levels. As a result, the effect of the harmonics in the grid or in the system is quite less. So in that, we look if we don't look at the initial cost if we look only the running cost, in those countries would be lesser than our cost, which
That is right.
finally distribution loss.
Correct. Because what will happen is, once if they choose a right equipment, they don't have problems generating out of harmonics. The trippings, amount of unwanted trippings or unknown trippings happening is less. Then that automatically saves a lot of money on their business and when it is running, isn't it? So in that sense, there is much of relatively lesser problems due to harmonics over there, because they are following a reasonable standard in those kind of ways.
Okay, thank you. Also, you use the word, harmonics is like throwing garbage into a system. Yeah. So each of these equipment is throwing garbage into the network and polluting the entire network. And finally, we try to put something at one point and try to filter it out. As a result, no, this is one way of handling, but the inefficient way of handling. The energy cost is also going up day by day. Now, getting energy itself, or we are talking more about sustainability. So it is the time for the government to seriously think to implement these modern standards and ensure that the products which is sold in the market are complying to the minimum levels. Am I correct?
I would say, more than the government, it is up to the users to come forward and say, I will follow this. If that comes in, then automatically government may not have much role in it because users themselves will clarify it. Once when we start policing these kind of regulations, they tend to find a different kind of a route. So it needs to come from the users. Consultants who are applying these has to apply these standards properly in their design stage. So then it could probably change the whole game.
Okay, that's great. That's great. But one last question from my side. Let's say, for example, in a new project, if all the devices are which are in compliance to the latest IEC standards with respect to harmonic emission are used, and in the same project if they are not used, what will be the cost implication over a period of, let's say, 10 years?
It depends completely on where you are in the position in the grid and how you are using your own equipments. I'll give you a simple example. One of the food industry which we came across, they had two big soft starters and few juicer, a VFD where to drive some of the juicers. Basically, it's a food processing industry. So they had a lot of trouble, and their VFDs had a lot of failures in their IO cards continuously. So they called the VFD guys and said, why is my IO cards failing? And then this guy comes and says, oh, this is because of surge and transient. You know what they did? They put surge suppressors at the incomer stage, at the main incomer in their place in 230 volts level. They put a lot of surge suppressors in various circuits. You know what happened? The IO card problem stopped. And then they started replacing surge suppressors every week. So the kind of the design has become such a way that you move the problem from one to the other side, but you don't get rid of the problem. To do this, implementing the right device, following the standards meticulously at the beginning of the project becomes very, very important. Otherwise, we will be only moving the problem. So when we have to say what is the cost effect, which can be more than 10 times what they would invest at the beginning.
So probably over a period of time, if we calculate the cost implication over a period of time, probably going for a good quality installation is less costly.
Less costly. Yeah. That's true. Good. It might be looking at as an investment at the beginning, but later on, when there is no operation. Today, I will give you an example in another example in Middle East. Before 2006, 2009, there were buildings with very, very high quality. Yeah. Later on, the more the number of buildings came, more number of competition came in, the quality also slowly reduced. So today, we go to a building and find there is no measurement possibility. We do not know, the meters don't work on the panels. We do not know what kind of harmonics, what kind of loading is available on the panel. So these are some of the common problems what we face. Had they chosen a right product at the time of installation, no one bothers to do it, change it during the operations. So then there is no data when they need it. So that is very, very important that we make electricity panels in such a way that we have the data also captured and stored somewhere so that it can be useful for us to maintain it over a period of time. Yeah, so that's very important. Okay. And you design a panel for 25 years and then the equipment inside the panel doesn't work for more than 10 years, which is not good.
Yeah, we'll go through some of the questions. There is a question from Mr. Omnath. Can harmonics lead to malfunction of electronic trip units mounted on low voltage circuit breakers? If yes, any case studies you have?
Okay. Okay, I will give you this case study. I was talking about looking at your video also on the RCBs. So I will also give you the same kind of a solution, similar kind of issue which I have come across in one of the hotels, where they use a big conference rooms where it is used for a lot of teleprinter or the monitors are used for every table and every chairs where they use. Yeah, so they had a problem of RCB tripping very frequently. They were only changing the RCBs 1, 2, 3. It was continuously failing. It was tripping. It will suddenly during a conference, one circuit would trip. And every time it is a different circuits. So they were not having a clue what was happening. They were actually using an RCB for a AC circuit. But since there is so much of electronic loads and lights in that particular circuit, it was actually type B and type B plus frequency, higher frequencies were making those RCBs trip erratically. So there is a possibility that low voltage circuits can have a potentially be influenced by harmonics and higher frequencies, and it can trip. So that's one case study which I have seen it myself, so that could be shared worthwhile. So
Yeah.
it affects the low voltage side. That's what I wanted to say.
Okay. So we have the next question from Mr. Purushottam. Up to PCC level, IEEE 519 for downstream level load side, which standard has to be followed for recommendation?
61000-2-4 is the thing for the equipment level. So at the point of common coupling, it is IEEE 519. And then at the equipment level, we can go for 61000-2-4.
I think this the IEC, this one is talking about the limits of harmonic emission by individual equipment.
Individual loads, right? Correct. Compatibility.
Say for example, let us say, for example, maybe a VFD or some kind of an LED light, or let's take it as two cases. VFD is to, let's say, 16 amps. What is the limit of recommended in the IEC, or as well as for LED lights? What is the limit of
No, it
emission?
is nothing to do with the LED lights as such. There is no standard to say that it is LED lights. It is the standard. Maybe I have to share the standard, which will say, 1 minute. Let me take this thing and give it to you with this information. IEEE 519, yes. So this talks about voltage, power frequency variation and harmonic up to 50 and transient voltages in IEC 61000-2-4. So it talks about power frequency, it talks about harmonics, it talks about there are limits for this for harmonics also in this particular standard. So we may have to open the standard to tell you which limits it works for. So
Okay.
it talks about the voltage, how much of voltage deviations are allowed, how much of dips and short interruptions are allowed over a 1-day period, and then how much of harmonics is allowed to come in or to come out from these equipments. So it talks about all the three cases in this particular standard.
Okay, that's great. So we have the next question from Mr. Rajan Menon. Is any sector mandatory to continuously monitor IEEE 519?
IEEE 519 is to be monitored continuously, because it is whatever you do as a test, it is done for 1 week. And then if you continuously monitor, because the loads are not going to be the same, the loading pattern is not to be the same, the dynamics of the upstream grid also changes. So it is always better to monitor continuously and know what is happening in your system. So if someone comes and monitors IEEE 519 for 1 week and then they give it, it is not necessary that every week the same results would come. Every week the results can change. So that's for that reason, at least IEEE 519 needs to be monitored continuously.
We have Professor Mahendra Chilikuri from Vellore Institute of Technology. He has raised your hand. Professor, you can ask your question, or you can have an interaction.
Yeah. Good afternoon. Can you hear me?
Yes.
Okay. I think you rightly mentioned just before that, this power quality monitoring for 1 week is only gives a limited understanding of what happens on the grid or at the customer side. And in fact, recently we have recommended to POSOCO that at SP solar power plants, the power quality cannot be monitored once a week for a year and then assume that everything is fine. So this has to be extended, especially at large solar power plants, to understand the power quality issues both from the grid side as well as from the customer side. But there is one more issue that I would like to highlight to all the audience. The power quality is not only at PCC. The power quality problem at the customer premises is another different issue altogether. and there is a lot of interaction between the solar inverter and the VCBs and the solar transformers taking place, leading to a lot of failures on the VCB sides as well as on the transformer side. And Hitachi recently came up with a transient suppressor solution inside the transformer, and we have not seen, how it will be going to solve the problem. That is one thing that I would like to highlight. One more point that I would like to mention here is that LEDs are emitting very high frequency emission, which is not monitored by anybody at this moment. Not
Yeah.
only LEDs, EVs and other equipment also going to emit this emission. And the harmonic emission factor, the THD, right now is only up to 50th, and it has to be changed to measure the emission coming from EV as well as LED and other inverters, so that the supraharmonics effects can be studied on the grid side or the customer side. And my question was, which I posted in the Q&A box, is that what is the provision provided at the customer side to do PQ monitoring? Because when we did the study at certain solar plant, there is no provision to measure power quality at any place. And then some of the customers, they are not agreeing to, allow the panel to be open, touched, and meter to be connected. And whenever they want to measure, they are measuring in a very non-safe way, like measuring at CT side or measuring at the meter side. And I have recommended to CEA that power quality measuring facility should be there at every customer side, so that anybody can just come in and plug in their meter without disturbing, without anybody objecting that we are going to disturb the plant, all these things. So unless there is a mandatory requirement for PQ measurement at the customer side, especially large industrial and commercial sites, there will be a lot of issues in monitoring, and a lot of people also don't want to monitor. And those who want to monitor, they are only monitoring for 1 week and assuming that everything is fine for 1 year.
Yes. Yes. In fact, I agree with you, because that's why I said at the time of the project, there has to be some kind of a mandate or some push from somewhere else, maybe from a consultant or during the project stage, to definitely comply to by putting good power quality meters at the different levels where they feel deem important. And then it becomes a lot of this data from these meters can be a very, very valuable data during the operations for the people to get benefited out of it. But that is still yet to come in India, and I hope this wise thing will dawn into every projects very soon.
Yeah, Mr. Hari, actually, I shared the standard IEC 61024,
Yeah.
which shows, I think you may be able to see the
Yes.
levels.
Yeah.
What is your say? Is it possible to explain a little bit more on this particular thing?
Okay. Say, for example, it talks about the limit compatibility level. So which means voltage tolerance related to nominal voltage in class A, that is in an industrial environment with less amount of, where the short circuit class A, class 1 and class B is again based on the where our loads are there in the grid. So in that situation, whether it is strong grid or weak grid, and when with very higher short circuit or a lower short circuit levels, then we have class A and class 2, class 3 differences, and then you have the limits for these places. So that is why you said we have a very clear difference for the voltage tolerance, voltage imbalance, and the harmonics. If you look at it, it talks about 5, 7, 11, 13, 17, and up to 49, 50th harmonic. What should be the percentage of harmonic that particular load can emit?
Okay, so finally, if we really think the products which we use in this application, this table 2 is not complied. Am I correct?
May not be complied. That's what I'm saying.
Okay.
May not be
Also,
complied.
I would like to just have a look on what is this class 1, class 2, class 3. Let me open the definitions so that it is easy for us to understand probably better. Class 1, one
Class
moment.
2 and class 3.
Just open it up.
Yeah.
I think it's already mentioned in one PPT. Class 1 means sensitive load.
Yeah.
Yeah, this is here it is, the explanation of class 1, class 2, class 3. Class 1 applies to protected supplies and has compatibility levels lower than those on public network. It relates to the use of equipment very sensitive to disturbances in the power supply. For instance, electrical instrumentation in laboratories, some automation and production equipment, some computers, etc. Okay, so class 2 applies generally to PCCs and to IP environment of industrial and other non-public power supplies. The compatibility levels of this class are generally identical to those of public network. Therefore, components designed for supply from private public network may be used in this class of industrial environment. So then class 3 is this class applies only to IPCs in industrial environment. It's a higher compatibility level than those of class 2 for some disturbance phenomena. For instance, this class should be considered when any of the following conditions are met. A major part of the load is fed through converters, welding machines, large motors, and frequently started load very rapidly. So basically, the definitions are very clearly given, and the table 2 is explaining the limits. Am I correct to read it this way?
Correct.
Okay, thank you very much. Let me stop the sharing of the screen. We have a question from Mr. What is the best standard for in-plant power coupling for harmonics?
I don't get this question.
Yes, I think probably we will go to the next question. What type of filters IEEE or IEC recommend for mitigation of harmonics?
No, there is no recommendation of filters in IEEE 519. It only says whether you're complying or not complying, and how the mitigation is done is purely an exercise with the consumer, and then the best part they will have to choose whether they need to go with passive filters or an active filter, and where is the location they want to put it. Actually purely depends on the consumer themselves.
Okay. On what parameters can we can differentiate whether strong grid or weak grid?
Okay, it depends on the short circuit level at the point of common coupling, and I would say that depending on the short circuit level ISC and the IL value, how much load, your average load you are taking. Depending on that, you are given allowance or limits on harmonics, amount of harmonic what you can generate. So considering that, there is nothing called a strong. Beyond this value is strong, and beyond this, less than this value is a weak grid. It is nothing like that. But as far as the IEEE 519 is concerned, it gives clearly between up to ISC by IL value as 20. This is the limit. 20 to 50, this is the limit. 50 to 100, this is the limit, and 100 and above, that's the another limit. So it very clearly defines the limit depending on how we calculate from the ISC and IL only. So higher our ISC value, lower the IL value, then you are at a very high, very strong grid. Whereas higher the ISC value and higher the IL value itself, you are at a weaker position in the grid. So it depends on your limit, varies based on that.
Okay, thank you. The next question from Mr. Dhanavat. Does capacitor bank at user end can reduce TDD and THD or just improve voltage profile only?
I would ask Ravi to answer this question if he is there. I'm not sure. Ravi sir, are you there?
No, probably if Mr. Ravi can raise the hand, then I can make him on. He's not there.
Yes. He is not there. Okay. But the harmonic can be potentially it is not suppressed in a capacitor bank, if I'm correct. But it can potentially only increase in certain environment with capacitors and inductors. Ravi has come in right now here. Ravi sir, can you please put some of your thoughts in this as well?
See, it depends on the available ISC at the installed capacitor location. we can check the resonance. So capacitor is prone for resonance. So we have to, unless we make the reactive power delivering system, that is capacitor banks, virtually as a inductive load, it is a possibility of resonance, and even with a fully linear load also, plain capacitor bank create the harmonic. So it is required to be the system connected with the series reactor with the adequate linearity. Unless there is a problem with the harmonic, virtually it will be increased. And otherwise also flashover of due to resonance also it is possible. So plain capacitor will not mitigate harmonic.
Yeah. Okay.
Okay, thank you.
Thank you, Ravi sir.
Thank you, Mr. Ravi. Then the next question: can you please explain how we can incept the TDD concept at design stage?
Uh, we will have to do a power quality study, proper power quality study, and say that this amount of harmonic should be reduced. We should understand the short circuit levels at the PCC. We should understand the load pattern, how much it would be. Say, for example, in a place where we have a very low short circuit value, and if our loading is also pretty high, then ISC by IL value is very low, and we are in a more of a weaker grid area. So these needs to be understand, and a correct power quality study has to be done before the inception of the project itself during the design stage.
I would like to add one more sentence into the answer as the first answer. First, you should use a product which is not producing too much harmonics. Then you measure
that is very much unavoidable in the present day circumstances, but still that's a good wish.
Because there is no point in the polluting and trying to clean it up. First,
It's like putting a garbage in front of our gate and then trying to clean up. It will never get cleaned.
Yes, exactly. So the next question: how do we say TDD unless and until you install the device at point of common coupling? The testing of the meter used should be mandatory for sorting 7 days with sample rate of 167 samples per cycle. Do we have in our regulation? Mr. Hari, I would say you can also read the question. It's a little bit longer question.
Let me also try to do it. 1 minute.
Amrit last.
1 minute. I'm just trying to see.
First question now.
First question. No, what are the scenario of consumer? Okay. See, 1 minute. Mr. Amrit, right?
Yeah.
Just trying to check. In QA, Amrit, 1, 2, 3, 4, 5. Yeah. How do we see TDD unless and until you install the device at a point of common coupling? Of course, we need to measure to understand what is the TDD. This is point number 1. And the device, wherever we are measuring, we should put the IL value also to calculate TDD. So the measuring device should have the capability to enter the IL value, and then it calculates the TDD value. This is point number 1. The point number 2 is the meters should be mandated for storing 7 days. Yes, the data can be either stored in the device or it can be exported into the computer as and when it is getting stored. So there is a possibility. Ultimately, you need to have 7 days of data either in the device or in the computer as a database. So that should be possible. Definitely, it is required. And with regards to the sample rate which we are talking about, as I said, there is no standard for number of samples per cycle. But it is very important that we have a reasonable standard or a reasonable samples per cycle. Say 167 samples is also sometimes it is good if there is a class A device with that. and then we should be in a position to take the readings with those measurement devices. That is possible. But ultimately, measurement of TDD is very, very important, and we need to measure and we need to find it out from a device.
Okay, thank you. Thank you. We have Mr. Jitendra Kumar Rathore. Mr. Rathore, you can unmute yourself and ask the question.
Yes, sir. Okay. Thank you, sir. Very nice presentation by doctor. Sir, my question is that regarding harmonic in India, or particularly I am talking about the Maharashtra, as a distribution company has injected the voltage harmonic to the consumer, and consumer are injecting the current harmonic in the system. So, is there is any regulations, or there is any means compulsion to install the power quality meter to the consumer, or are there any regulation in the abroad to the distribution company for framing the penalty or incentive? You can say those consumers, they are maintaining the, suppose they are maintaining the harmonic level, then they should be given incentive in the tariff, or those they are violating, they should be penalty in the tariff. So if such kind of penalty are proposed, or such kind of penalty is imposed by the regulation to the distribution company and compulsion to the consumer, then definitely the harmonic level can be reduced, because it is unnecessary. You can say the affecting the consumer, those are using the linear loads. And nowadays government, and we are also promoting the solar integration, and solar integration is just a DC source. And because of this DC source, ST consumers, those having the heavy consumptions, they are migrating towards solar. But there is not any regulations. So do you have any idea, apart from India, in abroad, in other countries, are there such regulations or penal action?
See, I got your question. See, it is very, very typical here. The IEEE 519 mandates voltage harmonic is the responsibility of the utility, and current harmonic is the responsibility of consumer. Yeah. For example, if a consumer switches off his power supply and checks the voltage harmonic, and if the voltage harmonic is high, he should take it up with the utility to say, your voltage harmonic, what is given is high, right? And if they use a legally compliant device like Class A measurement device, then they stand a chance to put their case into the utility in the right way. But now, unfortunately, what is happening in the name of regulation, utilities are trying to police only the current harmonics and not the voltage, which they are giving, right? Which we are responsible for. So there is a small thin line of difference which we need to fight it out and come out. But I think over a period of time, this will evolve. This is my opinion as such.
Yes, sir. Actually, what I'm asking is, there such kind of regulation apart from India, other side you have observed, or you have any case study whether the government has imposed the penalty? If you have that information, that you can share.
There is nowhere governments or the utilities are putting a penalty for harmonics. It is followed by the consumers. Only in India, we are policing this activity with the help of regulation. This is what I'm trying to say. So there has to be a shift in the way in which we are approaching the problem. So for us, if government says, I will penalize you, I follow. Otherwise, I don't follow.
Yeah.
So that's the major difference as such.
Okay, thank you, sir.
Can I come into this? Can I interpret this?
Taking their responsibility properly. So if every consumer is taking care of their responsibility, or properly do their responsibility, such problems will be automatically reduced, and life of the equipment will go up. The process will not be disturbed. As a result, the returns in an industry will be much better.
Yes. Mr. Gopakumar, I have one alternative to this one. Can I interfere with this?
Yes, please.
Yeah, see, policing, as Hari said rightly, policing is only applied to the consumers. On the other hand, there is no policing to the utility company. So, utility is also having the shared responsibility. There is no regulation so far applied. For example, consumer is injecting the current harmonic, okay, not exactly injecting. Due to the injection of current harmonic, system impedance gets increased. Due to the increased impedance, voltage distortion is also increased. This is a problem. Neighboring consumer gets the higher distorted voltage into their system,
System.
even the consumer is with completely linear load and getting the higher distorted voltage, he is facing the problem with the higher voltage distortion. He is going to be a victim in this situation. So in this condition, it is possible to penalize the higher injecting harmonic consumer. Utility is having the responsibility to reduce the system impedance and give the good quality supply to the small consumer. Am I correct or not? So utility is having the responsibility, and the IEEE 519, it is clearly given the guidelines regarding this. But unfortunate that there is no utility abide with this regulation.
Thank
Okay.
you. Thank you.
Thank you. Thank you. So we will take one more question and close the webinar for the day. The last question, probably we have a lot of questions in the chat box, in the Q&A. Probably all the questions we may not be able to take up, but further we can continue this webinar. Maybe the second session we can continue, and maybe the third session we can talk about the solutions, because here we are only talking about the problem. So solutions also should be discussed. Probably we will continue this program. So the last question, Mr. Kamlesh Kumar, at PCC, which value of ISE we should consider individual feeder of substation or overall value of substation ISE having many feeder? What are the scenario at the consumer level which can create voltage harmonics?
Yeah, the ISC values usually take into consideration the upstream transformers and the transmission lines what you have until the point of common coupling. So that needs to come from your upstream transformer and the impedance of the transmission line or the distribution cable or the overhead line, which needs to be considered. So you have an upstream transformer impedance and then short circuit level, and then you also have the cables and the either it is underground cable or overhead cable coming up to the point of common coupling, and then at that point of common coupling you still have a short circuit level which needs to be calculated. So that is purely a calculation from depending on how far you are from the substation which is feeding your loads. What are the scenarios at consumer level which can create voltage harmonic? The higher current harmonic you inject into the circuit, and depending on the upstream impedance, it can potentially distort the voltage waveform, and then that is why the voltage harmonic also increases. So that's another way of looking at it. Kamlesh, I hope I have answered this question.
Yeah. Is it possible we can take the one more question, the last question?
Yeah.
Mr. Rohit Khare, you can unmute yourself. So Rohit, you have raised your hand.
Yes, sir. Thank you, sir, for such a nice presentation. I'm Rohit Khare from this side, from IIT Kanpur. So my question is related to transmission congestion risk from the DISCOM perspective. How we can mitigate that kind of problem? And my second question is related to the total demand distortion, as you said, that because we are managing dynamic variability of the load, particularly with the increase in integration of the renewable energy sources and electric vehicle, which can exacerbate the total demand distortion. So how we can mitigate that risk? And my first was about the transmission congestion from the DISCOM perspective. Yes,
Can you elaborate a bit on transmission congestion? Because I honestly I have not heard about this. Probably then I can I would see if I'm able to reach out.
Transmission congestion is mainly when the generator is sending certain amount of power, which was tied up with certain power purchase agreement and with the bilateral input to the buyer. And due to the case, suppose the generator is generating the 200 megawatt, and due to the transmission congestion, it is not able to send that amount of power, not that amount of power into the grid to the buyer. So due to the transmission congestion, so what are the because at that same point of time, if we are trying to implement some new infrastructure of the overhead line, it is not possible for the in the short duration. So how we can resolve this problem, sir? Because this is a
So
most
I think it is a dynamism of the grid. I may be wrong, but I can also seek help if there is anyone who can answer this. But I think it is the dynamism of the grid which is actually creating the congestion, which means there is a change of impedance in the circuits on the all over the grid, right? So that is why it is limiting the power supplied by the generator to be supplied by the generator. So probably that needs to be addressed by the impedance. So utilities should always, or the distribution companies should always be considering this impedance on their system because of various loads and generators coming into the system. They should also be taking sufficient responsibility. I don't see any utilities or actually working on changing their the impedance of their system in a regular manner, because I see most of the short circuit levels what is given by many of the utilities at various points are same for the last 20 years, whereas this grid has grown very vast in the last 20 years or so. So that's how I see it, more dangerous from the utility side for not doing any action on that.
because actually my concern is this, because if I because someone told me about if we better forecast and we if we better schedule the power, this risk can be this risk can be we can hedge that kind of risk. But I think that we can if by just providing only if we are only just providing the better schedule and forecasting, we are
Yeah.
not increasing the capacity of the power, we are not increasing the strength of the power that can be transferred to the transmission line. So that's why it's a very challenging task that we
See, even if
Thank
we
you.
forecast, maybe some AI can help in future for us to do this. But it is very, very difficult to ascertain. Someone can forecast at one level in the network. They can forecast this could be my X amount of loads which can get added up in the grid, and what would be the impedance and things like that. But in actual, it may be different as well. So how forecasting is accurate also matters when it comes to these kind of solution. But some kind of AI could help in future, but I'm not very sure about it. Let's see. Let's wait and see on that.
thank you,
Yeah,
sir.
thank you, Hari, and thank you, Mr. Rohit. Apav sir has raised his hand. He is actually traveling.
Oh,
Probably, I don't know whether he will be able to speak. Apav sir,
Thank you, sir. Am I audible? Some noise
yes.
is it? Okay, okay. Okay, thank you. Uh, it's a very nice session, Haribala. My friend has given a very nice session. And there are two type of mitigations involved. One is mitigation for compliance of harmonics level as per regulation, or to be enforced by the distribution companies. Another thing is internal mitigation. That is, whether you are complying with the regulation or not, your own equipment are likely to failing because of higher level of harmonics emitted by the individual equipment like VFD drives or UPS as per 61000-2-4. So the thing is, the TDD, actually the mitigation is devised in such a way that the consumer is helped a lot, you can say. In fact, I have worked with Mr. Ravi and we have evolved a white paper on it. We can upload it in our another group. The thing is, if you meticulously see the total distortion, TPD, the numerator is THD, denominator is the load current. That is a percentage. If I have 30% harmonic, and if we come to the TDD, the denominator is the annual demand current. So if you have higher demand, then the 30% will be reduced by 15%. The consumer is having, always having, I can't say it's a manipulation, it's a statistical part that consumer can devise a reasonable base demand, that is the annual demand load, to comply with the regulation without anything, without doing any harmonics mitigation. That's one of the wisest thing the consumer can continuously do, and device is total device is annual demand to contain the TDD. So one more thing is the supplier's grid can't be made too strong and strong. It all depends upon the market-driven mechanism. When there is an industrialization taking place in a place, then it gets automatically strengthened by virtue of its power plant or the power transformer, the substation. For example, the 10,000 MVA is occurring in a 110 kV grid in Tamil Nadu at one place at IT sector. And the same 110 kVA, 110 kV distribution, it occurs 2000 MA only in a rural distribution. So how can we ask the distribution company to enhance the power transformer in rural distribution to 100 MA or 200 MA? It's not possible. It all depends upon the thing. It's a, as per Ravi's, it's I partially agree with Ravi's statement that the distribution company is responsible for voltage harmonics. Where these voltage harmonics coming into picture and affecting the other linear load people, they are not affected by the grid. It is because of load harmonics created by so many people in the grid, especially the consumers. The actually the grid do not create harmonics. They are all having linear devices because of EV and solar as well as power electronics. We are having so many pollution into the grid. We can't blame the grid alone. That's my point. I think we can have some more discussion the next. We can have some more webinar, another part 2, the next session to discuss much on it. I don't know whether I am audible during the journey, but what I can say is consumers are already liberalized by the harmonic mitigation measures enforced by the distribution companies through the central authority regulations. That mitigation available is you ascertain your total demand load, annual total demand, and you mitigate at the point of common coupling. We don't bother about the lower thing. But actually what happens when they find it difficult to cope up with the failure of EFD drives or sensitive drives, they automatically go for the harmonics mitigation at the lower side also. It's a compulsion. That's what I can say. I am not able to communicate. I don't know whether I am audible or not. Thank you, Mr. Gopal.
Thank you. Your point well made.
Thanks for Mr. Hari. Thanks for Mr. Ravi. Also, Mr. Chilikuri. Thanks for all the interesting questions. We have further, I think, about 16-20 questions are there. If we start answering each question, there will be another list of questions finally. Probably we will continue
this topic is.
Yes.
It shows
probably
how
we can continue this program as session 2, session 3. And I think there is scope for even including 1.5 hours each session. Probably 10 sessions we will be able to do. The next session we will have a panel discussion as Professor Chilikuri told. So probably if all are free, we can make it in the coming week. For the time being, thanks for all. Mr. Hari, if you have any conclusion, you can continue.
No, and I, as a conclusion part, I should thank the whole group, whole participants. It was very, very enthralling session for me because it was a lot of information which I also learned quite a few in this session, and then I'm happy to be a part of this group. And we will continue to interact. If there is anything, I'm there in the group, WhatsApp group itself, so you can address to me. Maybe I can also take up the other questions at a personal level. Yeah. Thank you very much. Thank you very much for the opportunity. Yeah.
By this, we end the program. Thanks for all the participants. Let's wait for the next week's program. Thank you very much.
Thank you.